Hi everyone, this is our last topic, convolutions. Convoluted, oh my god, what is this going to be? And let me motivate a little bit what we're trying to do here. It's a little bit of more theoretical usage, but although we will use it for certain nice calculations. So, but let me start from a simple example. Suppose we have y double prime minus y equals well, let me call it just ft, some forcing function. So how would we solve this? Well, with Laplace, okay? If we use the Laplace transforms, we would say, okay, we do this, and we do the Laplace transform of that, and we do the Laplace transform terms for that. Let's call that f of s. So this is the Laplace transform of little f, capital F, okay? And so we know that this is s squared y minus, and let's for simplicity take the initial conditions both to be 0. Now remember, in the formula for the Laplace of the double derivative, this is s squared y, and then there would be here an sy0 minus y prime 0. But for simplicity, I took these both to be 0, so it's actually not there. So that's even, this is just an example, right, to motivate. And then we get, this is just minus y equals capital F of s. So we solve for y, we see y is s squared minus 1 capital F of s. So we see that y is equal to f of s divided by s squared minus 1. Or, I'm going to write it a little bit weird in this way. Okay, let me write this actually in the back. So let's call this f of s times 1 over s squared minus 1. Normally we put it on one common denominator. Now, so far, these had been polynomials, okay? Or at least, sorry, if f was a polynomial, then this capital F was reciprocals, or these f's were exponentials, or they contained exponentials, or contained cosines or sines. So this would be a rational function. We would do the whole blah 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 on writing the partial fraction and then find the inverse. Okay, but what if this f of s is a much more complicated function? Okay, so it might, for instance, not be but this might not be a rational function, so we cannot do the partial fraction method. Okay, so but what is going on here? We have this function f that we know, and then this function that comes from our calculation from our left hand side, and we multiply them, right? That's why I try to figure this point this out. So this is a very special case of the case that we would have the product of two functions, okay? So we have here, suppose that if I write this, if I call this guy capital G of S, then we have this. So now is the question, suppose we know where this little f comes from, okay? This is the capital F is the Laplace transform of little f. But we can also calculate the inverse Laplace of this one, so this one comes from a little g, okay? So now you would say, professor, I know, this comes from f times g. Unfortunately, that is not true. So the Laplace transform of a product, I write a lot of question marks because we don't have formulas for that. So it's not that if we multiply these two that we get, so if you have to do the Laplace transform of two functions, you cannot just do the Laplace transform of that, the Laplace transform of that, and multiply. That's not true. Now, we are not interested in going this way, we're interested in going backwards, but that comes down to the same problem, right? Again, if we have a product, it's not true that this comes from f times g. Although we know that capital F comes from little f, capital G comes from little g, where does this come from? And this is now the motivation of a new product, really. We're going to define a new product. So convolution is actually a product. So the convolution product of two functions of f and g. So f and g are functions, let's say in T, defined on a domain continuous or piecewise continuous, etc., but we kind of ignore all the constraints. that have to be put on this f and g. Not every f and g can be done here, but the ones that we deal with can be done. Okay, at least on a certain domain that we then again not specify. This is an introduction to differential equations. If you take a high level course, then you would pay really attention to these things, because there are certain important features of this, where that's actually the harder part of differential equations, but we're skipping that part. Okay, so f and g. So I'm going to drive a product being times, right? But it's not the actual product, and therefore we use a different notation, star. Now, some of you, if you take linear algebra, you have heard about the dot product and the cross products, and so you might have seen products elsewhere in other courses. If you have taken abstract algebra, then you know that this comes from like a general theory of algebraic structures with a product. But okay, that doesn't matter what it comes from. Here's our definition, and it will be an integral, but not an opposed to Laplace, it's a proper integral with endpoints 0 and t. Of course, the result has to be a function of t. It cannot be a constant, right? This has to be, again, a function. So that's the variable t here, and that's why we integrate from 0 to t. That's just a choice one has made. And once we have stuck to this choice, so you can, let me write down what the insight is. That's perhaps more telling. It's f, z, g, t minus z dz. In the book they use a tau instead of a z, the Greek letter tau instead of z, but I think it's perhaps a little bit weird for you, so let me use z just as a variable here. So notice what has happened here. We do actually multiply f and g in some sense, but in a twisted way. So this is z, but this is some kind of twist of g. Okay, now be careful, it's not z minus t, it's t minus z. Okay, it's in that sense it's not truly a shift, it's even a shift and a reflection, if you want to think about it, what the graph is. And this t is going to be the variable here, right? So that is what we call the convolution product. Now, be warned, these are not easy to calculate, at least for complicated functions. But let's do this for one function that we know, and I'm going to take for f to be e2t, and let's g to be e to the minus 5t. Okay, let's see what this would be. In this case, the calculations are not hard. Okay, so let me write it up here in terms of the star, right? So what we're interested in is e2t convoluted product, the convolution with e minus 5t. Okay, that is 0t, and then f, that was now so now we have to learn to use this formula, right? Z, that means we have to replace the variable t by the variable z. So this becomes e to the 2z. What happens here? This would be e to the minus 5, and now we plug in, we replace the variable by t minus z. Okay? And then we integrate. Z is the integration, t is not. So let's see what this means. Well, since these are two exponentials, we can put them together, right? So this e, we have a 2z minus 5t plus 5z, right? You add the exponents, dz. Now, so this would be 0 to t, e to 7z minus 5t dz. Now, let's split this. The terms that have a z in it, that is the terms with a z in it, and then these are the terms without a z. What does that mean if there's no z in that term? That means it's a constant as far as this integral is concerned, so we can bring them out. So e minus 5t becomes a constant in this case. A bit surprised. It might become, you have been told in Calc 1 and Calc 2, don't do this, be careful, you cannot bring out something with a variable in there. No, because, true, but the variable is not z. You cannot bring anything with z outside, but anything without z can be brought outside. Now, this integral is very easy, right? This e minus 5t, and then what is this? E to the 7z divided by 7, compensation by 7, right? Evaluated between t and 0. Okay, this would be e minus 5t times, let's see, if I plug in t, I get e 7t over 7, minus, and if I plug in 0, I get 1/7. Correct? Okay. So what is this? If I multiply this out, I get e to the minus 5t to e7t. Well, the exponents add up, and this e to t over 7 minus e to the minus 5t over 7. Okay. Okay, so that's that. Now, let's look at this is the convolution product. Now, what is the Laplace transform of e to t? Let's write that down. You know what that is. That is 1 over s minus 2. The only thing it does is shifting, and it shifts, well, there's no power of t here, so we get just 1 over s, or s minus t here. What is the Laplace transform of e minus 5t? That was the other one, right? Yeah. That is 1 over s plus 5. Okay. What is the Laplace transform of this guy? Yes. Well, that's same thing basically, right? This is this guy minus 1/7 1 over s minus plus 5. Okay. So that is that. This is this, and this and this. Now, bear with me. What I'm going to do is multiply these two guys. So I'm going to multiply these two Laplace transforms. So get 1 over s minus 2 times 1 over s plus 5. Okay, that's a partial fraction. Okay. So we know we can write it as a times s minus 2 plus b times s plus 1, and Heaviside tells us very quickly how to do that. So a is what we do. We take s minus 2, s plus 1, s plus 5, sorry. We evaluate, we scratch out this factor with a is on top of, and we plug in 2. So this 1/7. Okay, so a is 1/7, and what is b? Well, let's copy it again. There's not really much going on here. So s is 5. Now, but this s is -5. S is negative, right? The root is -5, right? Sorry, that was s is -5. We scrap out the s plus 5. We plug in s -5, so get -5 -2 is minus 1/7. Okay, so this partial fraction is 1/7 over s minus 2 minus 1/7 1 over s plus 5. Wait a sec, this is the same as this guy. So let's see what this means. Let's write down what was this. This was the product of e to t, the Laplace of e to t, and the Laplace of e minus 5t. What was this guy? That was the Laplace of the convolution product of these two. So we were able to calculate the Laplace, the convolution product, and even we can calculate, we see that the Laplace of the convolution is the product of the convolution, of the Laplace. And this is the general formula. So this is the big theorem, if you want. I'll box it. The big theorem says that the Laplace of a convolution product is the Laplace of f times the Laplace of g. Okay, so let's go back to this particular example that I had here. Where was it? Here. Let's now see how can we use this here. So we had y equals f of s times 1 over s squared minus 1. Okay. And we needed to find the inverse Laplace transform. So we're going to basically do, what does this tells me? Okay. This one we know it came from little f. So this is actually this guy. This one, okay, let's write it down what it is, right? What is the inverse Laplace of this guy? So the inverse Laplace of 1 over s squared minus 1. Oh, it's a partial fraction, so I'm going to have to write it as, yeah, I wish I had to. I hope so far we haven't used anything. I'm going to make my life a little bit easier and put a plus here. Okay, so this becomes a plus, okay, this becomes a plus. Nothing, it was just an example, right? Now I'm working on the example, but now I'm going to do it with a plus here. Because it's going to be a little bit quicker. Because what is this? Well, that's the sine t, right? That's just, the omega is 1, a is 0, so there's no exponential here, so that's sine t. Okay, so what does this tell me? So let me recapitulate. This comes from this original function f that I had, which I didn't specify what it was. This is the Laplace transform of sine t. And now we have a product. So what we have here is this: the Laplace of f, ta-dum, times the Laplace of g sine t, ta-dum, and we multiply them. And that's the Laplace of the convolution product. So we know that this is the Laplace of f star sine t. Okay, so capital Y is the Laplace of f star sine t. That means that little y is the inverse Laplace, which is the inverse Laplace of Laplace, that's just the original function. So our solution is f star sine t. And what is f star sine t? F convoluted t. Well, by definition, that is what this is. Fz times sine t minus z dz. So it's an integral that you have to solve. But I have to warn you, these are not easy integrals. The problem comes from the fact that we have this kind of shifting here. If we would not have a shift, then we can do this. But this is where it gets hard. And so in this chapter, most of the time we're just going to leave this as is. So what it does, so in other words, what this convolution product does is it allows us to solve the differential equation up to an integral. Now that might sound like, yeah, okay, but okay, that's what differential equation is. If you're happy with that, then why do we do anything at all? Well, that's not, even if I write down this let's say with f, if f is say ln of t or something like that, even then I would not even, without this technique, I would not be able to say what y would be unless I use it as a power series. I would not have any technique to solve it. So now at least I haven't solved it, but I've reduced it to a type of integral, and then this becomes a study on its own. These are called actually convolution integrals of this form, because they are so, they appear in whenever you have a differential equation like that, and I repeat, these second order differential equations with constant coefficients appear in harmonics, in motion, in law, in the laws of cooling, in LCD circuits, and in many other applications. Okay, so now what I want to do, a couple of things. First of all, it is a product, right? And well, you kind of would expect that doesn't matter in which order you do this, right? Right? Fs times gs is the same as gs times fs, right? And true. So it is true that f star g is equal to g star f. But that is not obvious, because let's write down what this would mean. This, by definition, would mean gz ft minus z dz. But it is not so hard to show that these two integrals are the same. A priori they don't look the same, but by what they call a change of variables, you can show that they're the same. I'm not going to spend time on that. I do want to kind of explain a little bit. I wanted to show you that this formula here, I want to justify. So I want to justify this formula. So justification. And what does that mean? Well, I'm going to calculate the Laplace transform of f star g. Okay. Now be careful. We are now talking in very general terms. Okay. I do it once just so that you see how these things work. But okay. So I want to calculate this guy. Okay. By definition, the Laplace transform is an improper integral. E to the minus st f star g t dt. So far so good, right? But now what is f star g? Well, f star g is actually also an integral. But it's an integral inside an integral, right? So what does that mean? This is the integral from 0 to t fz times gt minus z dz. That's just using the formula of the Laplace. the convolution product. Where is it? Here. Should perhaps box this too. This box is in green. Okay. And the other formula of the Laplace was the original formula that I copied, right? Now this whole thing is this integral, that is this guy, and then there's the dt. And now there is a trick that I'm gonna wave a little bit my hands and saying that I can switch the order of integration. But I have to think a bit about what this is. So let's see here. We have two variables, right? The variable t and the variable z. And the variable t goes from 0 to infinity. So this variable, I'm going to go all the way here. What is the variable z? The variable z goes from 0 to t. Okay, so this is the line t equals z. And so this is the line t equals z, right? And my variable z, say, suppose for a fixed t, what is the, let's look at for a fixed t here, what is the value that z can take? Well, it goes from 0 to t. So it goes from 0 to t. Okay? And so, and if you now take all the possibilities, then you get this region, right? So all the t's and z's that appear in here lie in this kind of triangle thing. And there's now a theorem, it's called Fubini, that you can switch the integral signs as long as you integrate over the same. So what does it mean? We're gonna do this here. Wait, let me see. I have to do it in the right order. So what I'm going to do is. Sorry. Yes. Yes. So, sorry, let me do it in two steps, because otherwise it might be a little bit too quick. So, okay. First of all, what about this one? This integration with respect to z, so there's no harm to bring it inside. So, let's bring it that inside so that our integral signs come next to each other. So, we get e to the minus st fg gt minus z dz dt. Okay, in this order. So the order is this implies a certain order. You would say, yeah, but I mean, it doesn't matter because it's multiplying. Yeah, but this is integration, right? It's not really, these are parts of the integral sign. This belongs to this integral sign, this guy belongs to this integral sign. So, okay. So now is the switch that I said. So instead of, so I'm going to switch the t and the z. So this integral now will be all the possible values that z can take. So what can z do? So now let's look at a fixed z. What are the values that z can take? Well, anything that goes here, right? It has to lie in the right-hand side triangle, in that lower triangle. So this means z can start from t and can go to infinity. So from t to infinity. That is all the possible values that z can take. Okay, now what about t? Okay, so for this fixed z here, so we have fixed z, what are the values that t can take? Well, everything from anything, right? From this, anything from, sorry, I'm saying it wrong. Oh, sorry. I was a bit too fast. Let me repeat what I said. So ignore my previous statement and I'm going to go over it again. What are the values that z can take? I'm sorry, I was confused about it. Z, well, in principle, there are possible z's everywhere. Every z here, no z's can here. There is no point, nothing in this thing corresponds to a z that is negative. But if a z is positive, there are points here, the blue ones. So any z is allowed here. So this means that z can go from 0 to infinity. Sorry, that was my mistake. And now, once we have fixed z, that's what you do, right? So first we have z, let z range over whatever it can range, that's from 0 to infinity. Now we fix the z, and now we look at the limitations that t give. The limitations are this one. So t can start from this value, which is z, and go up all the way to infinity. So it starts from z and can go all the way up to infinity. Yeah, now I have it correct. Okay. Yeah, that is very often in this switching of, so dt dz, sorry, I had it written right a bit again. The switching is, the endpoints are sometimes tricky. When your domain is not a nice square quadrant, but like a half a quadrant, like a triangle like this. But now, let's now analyze this inside integral here. So let's look at this integral now. It's an integral with respect to t. So whatever does not depend on t, I can bring out. Now, let's look at the three terms. This one depends on t, this doesn't, this does. Okay, a priori, right? We don't know exactly, but it looks like it. So only the middle one I can take out. Sorry, I want to do this in black. So this is equal to 0 to infinity. I bring out the fz, and what I'm left is z to infinity, e minus st, gt minus z dt, and then we have a dz here. Okay. Let's do in here a change of variables. Let's do x equals t minus z. Okay. So what does that mean here? So x is t minus z. So remember, t is original variable. Z, it is a bit hard to think about, right? But when we inside here, z is a constant. So t is my variable, and I'm going to do a new variable x. So this is a substitution. This is a substitution. Keep in mind, if let me call it perhaps u. You're more familiar that if instead of x, let me write u here, because that's what you normally do, substitution, right? So your substitution, u is t minus z. Okay. Now it's a definite integral. We always say that if you do this, this is t, this is u. What if t is z? What is the value of u? So we're going to replace everything by, so du is equal to dt, right? So that is okay. And the rest we will see what happens. But let's first look at the endpoints, because it's a definite integral. In substitution with the definite integral, you also have to change the endpoints. So if t is equal to z, the lower endpoint, then u is equal to, well, z minus z, that's 0. If t is equal to infinity, what is, if t is infinity, what is u? Well, infinity minus something, that is still infinity, right? So the new endpoints become from 0 to infinity. Okay, so these are the new endpoints for u. Now, let's replace. U is t minus z. We can write this also as u plus z is t. So now replace everywhere that we have a t by this u plus z. Then t minus z is u, so this is just g of u. And then dt is du. Okay, so this is what I have. Okay. Notice that z is a constant here. So in this guy, I can actually split. Okay, so I'm going to write this. I'm only working with the inside part now, right? So I'm working this part. There is still more to do. But I'm going to split this e as e minus su times e minus sc. We do this very often with exponentials, right? And then which one can go out? The one that doesn't depend on u, which is this guy. Okay, so this e to the minus sz from 0 to infinity, e to the minus su gu du. Now, professor, if this u would have been a t, then is this not just the definition of the Laplace of g? True, yes. If you just, instead of t, what we normally have, now write u, you get the definition of the Laplace of little g. Okay, so let's now put everything together. Remember, there was still this outside parts that I have not done. So this is equal to, from 0 to infinity, fz times, this guy, don't forget him, e minus sz lg dz. Now lg, what does lg depend on? Well, lg is a function of s, right? Remember, it's a function of s. Or Laplace transforms are always functions of s, right? This has become a function of s, which is not z, so I can bring that out. It's a different variable. So this is lg. This one does not depend on z. These two do. And what I'm left with is this. And I'm just going to write it in this order because, what is this? the formula for the Laplace of f just by replacing t by z. So this is the Laplace of g times the Laplace of f, and that's exactly what we want to prove, because the product of two functions, it doesn't matter in which way you write them, right? So we prove that the Laplace of the convolution is the product of Laplace. So this is, I wanted to give you an insight of how these things work on a theoretical level, and this would be something for a higher order level course that you would. There's still details missing here, by the way, but this is really the scope of what we can do. Okay, so let's look at one. I want to do an application here. So let me do this one here. We did this one. Okay, so we do y double prime plus 2y prime plus 2y equals f, and we're going to y0 equals 1 and y prime 0 equals 4. I'm just taking some numbers here. Okay, so what I want, so what is the goal in this chapter, at least for this part, for these differential equations, is to find a formula for y which only contains a convolution integral. Okay, so how do we work on this? Well, we say f has Laplace transform capital F. Okay, that's just, we don't know what little f is, so for now we write capital F. Then we take the Laplace transform there, so Laplace y double prime plus 2 times Laplace y prime plus 2 times Laplace y, little y, that's now capital F. Okay, and we called capital Y the Laplace of little y. Okay, so this was s squared y minus s times y0, which was 1, right, minus y0 prime. I'm just quoting the formula, look it up, right? 2 times, this is sy minus y0, that was 1, plus 2 times y is capital F. Okay, so let's expand this. So this minus s minus 4 plus 2sy minus 2 plus 2y equals capital F. So okay, so this is s squared plus 2s plus 2y, and then we have a minus s minus 6 equals capital F, so we get s squared plus 2s plus 2y is capital F plus s plus 6, and so solving for y, this is capital F times 1 over, I'm going to write it this way, okay, plus s plus 6 divided by s squared plus 2s plus 2. Now, and this is where the technique comes in. What we need to do, we know capital Y, and so to little y we have to take the just inverse Laplace. And there are two types here now. This a type that is something that is very familiar to us. This is a partial fraction. We have to write this as a partial fraction. That's the only thing we need to do here. This one is a type we don't know what to do with, because this capital F, we don't even know what it is. So this will give me the integral that I was talking about. I'll show you later what I mean. So we're going to deal with these separately. Now, in any case, in both cases, I have to look at the denominator. So the denominator is s squared plus 2s plus 2. That's actually quadratically reducible, so we have to complete the square. I mean, you can try a little bit to find the roots, but you'll see immediately there's no roots, no real roots. So to complete the square, remember that is s squared plus 2s, then you add the number here, divide the 2 by 1, by 2, you get 1, and square it, you get a 1 here, and then you subtract by 1. So this is equal to s plus 1 squared plus 1. Okay, so y is equal to f over f times 1 over s plus 1 squared plus 1 plus, and now we have this fraction here, s plus, s plus 1 squared plus 1. So, as we said, we're going to deal with this one in a totally different way than this one. This one we will use convolution. How? Well, we know this comes from little f. We also know where this comes from. The sign, right? It's just going to be an e, and there's an e, a shift and a sign. And so what will be the inverse Laplace then be? Remember, so this is where you have to think of, we have the formula here, this formula, but perhaps the way that we use them is this way, that if you take the inverse Laplace of a product of two Laplaces, then that is the convolution product. So that is how we're going to use this. Okay? So let's perhaps write that down here. Okay, so this will be what? Okay, I have to take the convolution of the inverse Laplace of this convolution, and the inverse Laplace of that, what we said was, well, let's see, what is it? Let's write down what it is. Be careful. We have to analyze this a little bit. We have that omega is 1 and a is negative 1, right? Minus minus, okay? So this is e to the minus t sine t. It's a sine, okay? And so what is this? Let's write down the definition of this thing, as namely show that it's an integral. This is fz times e to the minus t minus z sine t minus z dz. Okay, that's just writing on the formula here, using the formula, the very first formula, I guess, here, the green one, okay? Now, we don't know little f, but possibly there would be a little f here, and then we have a real integral here. So that's the point. We have reduced this part to a simple integral. Sorry, I want to. So this part to a simple integral. Okay. Now there's a second part here, so we have to still do this plus. There's something here. How do we do that? Well, here we have to do the partial fraction. So how does that go? Well, we know the partial fraction is going to be a s plus 1 plus b over s plus 1 squared plus 1, right? But it's actually always there. This is actually the partial fraction if I write it as s plus 1 plus 5 s plus 1 squared plus 1. So we don't actually have to work out the partial fraction. It is the partial fraction if we write it, if we split it up the right way. And so we can now, this therefore splits as, so I'm going to keep writing plus here, as s plus 1 over s plus 1 squared plus 1 plus 5 s plus 1 squared plus 1. And each of these we have to take the inverse Laplace here, right? That's what we're going to write. Oh, okay, sorry, I should not write equal here. I have to be careful with what I wrote here. So this is not equal. So, yeah, okay, sorry, let me move this away. I don't want to write something, no, I cannot do that. No, I do this, right, so, sorry, a little bit. I want to fix this a little bit, so. Let me move this down a little bit. Okay, and I should also move this guy down. No, move. Sorry. So no, let me not do anything with it. Sorry, I just don't want to write something wrong. The plus here is wrong. So I'm just gonna here do it on top here. Okay, I'm just gonna already do the splitting on top here. Okay, you saw what I did, and I'm gonna just write it here because I don't have space anymore. So I'm gonna write this as s plus 1 plus 5 times. So okay, so I copied these two terms and wrote them again like that, because the next line is the inverse Laplace. Sorry, I wanted to make sure that we write these correctly. So we take the inverse Laplace. The inverse Laplace of this product here is the convolution. The inverse Laplace of this is just, well, we know what it is right here. Omega is 1 and a is negative 1 in both cases. It's the same guy. So this will be plus. This would be cosine, right? And there's an e minus t, cosine t, and plus 5 times e minus t sine t. Okay? So we don't need to do this partial fraction, and so the answer would be, therefore, this is the answer, sorry. This, so the plus, let me copy these two guys here that I did them. Plus e to the minus t, cosine t, plus 5 sine t. So this is my solution. And that is what you're going to do in the homeworks. Most of the homeworks will be asking you to do this. So it will contain a true inverse Laplace and together with an integral. And write it as an integral, not just as a convolution product, as an integral. Okay, I want to do one more application, neat trick. So a neat trick. Suppose somebody asks you, okay, calculate for me this guy. You say, okay, all right. It's a polynomial. T is as far as the integration concerned, a constant. So it's a polynomial in Z. Oh, I expand and then do the product rule. There's nothing difficult here. True, there's nothing difficult here. You can do it. But expansion. Sometimes you say, professor, but then perhaps substitution, right? Substitution is going to make it easier. No, think about it. If you substitute, so you want to make this a simpler variable, say u, but then this becomes a difficult thing. This becomes u plus t, and so you still have to take the 7th power of that guy too. So this is easy to do, except for the fact that you have to do a lot of algebra. So now I'm going to show you that you can do this actually much better. Let's see. This is, and you have to recognize this is what we call an involution integral. It's actually involution product of two functions. Let's figure out what are the two functions that we are taking here. So, there's the 7th power and the 5th power, right? And that, remember in the involution product, convolution product, was the formula? One function, we have just the variable, and the other one is t minus z. And so that's what we're looking for, something like, that's exactly what we have here. One is the variable and one is t minus z. Okay, so this is the f and this is the g. Okay, so f of t is just t to the 7th, and g of t is just t to the 5th. You agree with me? If you take this f and this g, then this is f star g. Okay, or more explicitly, let me write it even more explicitly. Let's not bring in the f's and g. Let's write it. This is t to the 7th star t to the 5th in this order, but we said the order doesn't matter, and that's because you can do a so-called change of variables. But let's not concern ourselves with it. Write it in this order. This is that. Okay. So now we're going to use the following. I'm going to say the Laplace transform of t to the 7th star t to the 5th. That's the Laplace transform of t to the 7th times the Laplace from t to the 5th. Correct? Okay. What's the Laplace from t to the 7th? That I know, Professor. Can I do it? Okay. That's 7 factorial over s to the power 8. Right? That's just the formula. And what's the Laplace from there? It's 5 factorial over s to the power 6. Okay, yeah, okay, good. So what are you going to do now? Well, okay, let's multiply it. 7 factorial, 5 factorial, and then it's s to the power 14. I'm going to write it in a bit weird way. I'm going to write it as 7 factorial, 5 factorial, and I'm going to put here 13 factorial s to the 4th, and then divide by 13 factorial here. That's okay, right? Why? Because this... So, notice what I'm saying. I'm saying that the Laplace of this guy is this, that. So the Laplace of this function is this. But I know what the Laplace of this function, the inverse Laplace of this function is. So I'm going to now take inverse Laplace again. So inverse Laplace. What do I get on the left-hand side? Well, t to the 7th star t to the 5th, right? That's just cancelling the Laplace. What do we get here? Well, 7 factorial, 5 factorial, 13 factorial, inverse Laplace of 13 factorial over s to the 14th. I forgot the 4 here. And I wrote it specifically this way because this is, what is this? T to the 13, right? Right? This is exactly what t to the inverse Laplace of, or the Laplace of t to the 13 is exactly this. So we find this is 7 factorial, 5 factorial, 13 factorial, t to the 13th. But this convolution product was what you wanted. Look, I gave you the answer. This is what this integral comes down to. You might be like, wow, how come it's so simple and no simple? Because there's a factorial there. This constant I would never have guessed. And then the power t to the 13. Yeah, this looks very weird, right? You wouldn't think that if you would expand this whole thing, there would be a fifth power, fourth power, third to 12. Oh, this would be a horrible thing, right? A polynomial of degree 12 up to degree 7, or yeah. So in each of these terms you integrate, and then you have 6, 7 terms, and you plug in t and 0, and magically everything cancels, and only this one survives. But that's what it is. The theory tells you that's what it is. Okay, that's what I wanted to say about this. And so in the homeworks, you're going to get something of the two types of homeworks, really. Well, calculation perhaps. No, I don't. Let me see what are the homework problems here that I was going to... Oh yeah, so perhaps I should look at one example here, so just so that you have the homeworks ready. So for instance, they say, what is the Laplace transform of, and then they give an integral. So I will do an example. 0t z e to the 3 z sine 4 t minus z. Okay, dz. Right, sorry, let me see, make me sure that I copied it somehow correctly. Okay, so find the Laplace transform of this guy. Okay, so first of all, we have to see that this is a convolution product. That was the same thing here in this application, right? Where we noticed that there is this part of the function, part of the integral contains z, and other part is based on t minus z, and so we have the same thing here. So we just split them. So this is t, and now, but I'll call both variables now t e3 star sine 4t. Let me. I write it down that it's perhaps not immediately clear where this comes from, right? So let's think about what would this be? What is this thing? By definition, you take the function and replace z. So remember, this is f, and you write fz, that is fz. And then you take this function and write g t minus z. So you replace t minus z. Okay? So in other words, this part comes from replacing t by z, this part comes from replacing t by t minus z. So that is how it has to work. So in the convolution product, one, you replace a t by z and you get that factor, and in the other factor is obtained by replacing t by t minus z. Okay, so this is what this is. And now we do exactly the same thing as we did in the previous case. So, yes, so now we take Laplace transform of this guy. Okay, so the Laplace transform of this guy. So okay, yeah, so let me write it here: t e3t star sine 4t. So we take Laplace transform of this guy, and we know by the formula. So this is the convolution theorem. That was the pink one, or what color did I make it? This is the pink one, right? This is called the convolution theorem. So I should perhaps say that because we use it, and when you use things, you should say what you're using, right? By the convolution theorem, the Laplace of this I'm trying to calculate what I'm doing, right? I'm trying to calculate this thing, okay? No, we need we need the Laplace transform of this thing, right? Sorry, they ask you the Laplace transform of this function, okay? So this is the Laplace transform of this function. So they ask us to calculate this. Okay, let's do that. We know by the product formula, the convolution theorem, that this is the same as that. Correct? Okay, but we can calculate the Laplace of these things very easy. This is because the t is 1 over s squared, and because of the 3, it's a shift by minus 3. So it's s plus 3 squared. Okay, and this one is it's multiplication, right? That sign, what is omega, is 2 here. Omega is 4, sorry, omega is 4, right? Omega is 4, and there's no shift, so we get s squared plus 4 squared is 16, and it's a sign, so we get on top the 4. So that is the answer. So it's actually very quick, right? This problem is this type of problems, they ask you to find the Laplace transform of this guy, okay? Which only thing you need to do is recognize it as a convolution product, use the convolution theory to calculate each separately and multiply them. And so this is the answer. This is what they want. Now, so what you really would like to know is the inverse Laplace of this thing, right? You could try to calculate the inverse Laplace of this thing, and in fact this is possible, right? Because this can be written as a partial fraction. It would be quite a lot of work because it's quadratic reducible here, and this would factor 3. So we would have an A, B, and C for the powers of s plus 3, and here we would have a ds plus e. So we have 5 unknowns, and it would be, you need a little bit of linear algebra to solve this. But in principle, we can find the inverse Laplace of this thing, and the inverse Laplace would then be this thing. So we can use this to calculate this integral, but in the question they don't even ask you to do that. They just say, give me the Laplace transform of that. So understand that question correctly. That is question number 2. I'm not going to assign too many homeworks. Okay? All right.